Questions about anything from last time? Or about anything? Yeah.
Are you allowed to use any hints in the homework?
Well, yeah, what do you can ask? Go ahead, ask.
Well, like on the last one, so like on problem 18 in section 1.2, like on the homework, I was just wondering like how to approach solving it. But like this is like the question that the office hours do that.
Well, what was the problem about? Is it an inequality one?
Yeah, so this 1 over the square root of 1, plus 1 over the square root of 2, 1 over the square root of n is greater than the square root of n.
Okay. But you need to use the induction hypothesis. Yeah. Anybody get anywhere on that one? Yeah, how'd you do that?
So for that one, I sort of just had the sum from 1 to 9 as like just a quantity, and I put that on one side of the quantity, and on the other side was square root of n.
Uh-huh.
So once we have that, that's like the first part of the induction function.
Uh-huh.
And then you can add square root of 1, like 1 over the square root of n plus 1 on the left side. Then on the right side is square root of n plus 1.
Let's see, what is it? Is this going to be less than 1 over n? Is that the deal? What is it?
It's greater than the square root of n.
It's greater than the square root of n. Why don't we talk about this on Piazza? And it's okay to sort of throw out ideas. Let's do that. That'd make a good way to start talking about it on Piazza. But the key will be to use the induction hypothesis rather than, this kind of looks like, integral test or something that you could prove from first principles, and probably it is. But if you're going to use the induction hypothesis, it's going to involve monkeying around with inequalities. Other questions? So I'll suggest we talk about it on Piazza. That's what Piazza's for. So today I'm going to talk about a wonderful thing about thinking about how big an infinite set is. This goes way back to George Cantor, who first started realizing some of these things were subtle and really interesting. And so I'll start out slowly here. Everybody knows what it means to be finite, for a set to be finite. It means you can count the elements. So a definition, a set S is finite if you can count it. So what does it mean to count something? Well, if I'm going to count, this set's 3. It's 3 elements. This set's 4. If I was going to try to show they were the same size, I would try to line them up and see if they line up. And the first 3 do, and there's one hanging out. So this set's bigger than that set. So everybody has the feeling like that about the size of sets. And so instead of lining it up with your fingers, you run out of fingers real quick, we're going to line it up with the natural numbers. So it's finite if, everybody in math likes to use this symbol for exist. If there exists a map from 1, 2, 3, etc., out to some n to S. And that map should be 1 to 1 and onto. It's like counting the set with your fingers, except your fingers are the natural numbers. Okay? And a fun fact that you can prove using the well-ordering property of the natural numbers that we mentioned last time. This n is uniquely defined. So a thing to note. To demonstrate that from first principles, like the piano postulates, you have to sit down and play games a little bit. I'm not going to dwell on that kind of thing. N is uniquely defined. Determined by this property. And we call it it's sort of the cardinal number for phi. It's how big the set is. It's the number of elements. And so it's well defined. Also sometimes the cardinal number, cardinality. There's two kinds of numbers. Cardinal numbers, that sort of measure size, and ordinal numbers that measure the order of something. Okay, so you'll hear those words, especially in certain books. We use cardinal numbers to describe the size of something. We don't have cardinal numbers for infinite sets yet, but that's what Cantor was thinking about. So let's see, that's what it means to be finite. And if obviously, if something is not finite, then it's infinite. S is called infinite. If it is not finite. Duh. Which means it's infinite if it can't be put into one-to-one correspondence with a 1, 2, 3, 4, 5 out to n. So that means no phi from S to a subset for any n. Okay, so those are the basic definitions for today. And Cantor started thinking about a big question. Are all infinite sets sort of the same size? So, are some infinite sets bigger than others? Turns out there are some big ones out there. In fact, I'm going to show you that you can there's arbitrarily big ones. Are some infinite sets bigger than others? Well, let's start out with some examples. I should test out my colors today because I asked somebody to work on them. Does that look green today? Greener than yesterday? Not much. Okay, I'll switch back to black only. Well, let's see. The simplest example to think about is that let's think about the natural numbers and the even numbers. Let's see, the even numbers would be 1, not 1, 2, 4, 6, etc. And if you're going to describe those, you'd say, oh, those are 2 times n, as n goes from 1 to etc. So this is 2 times 1, 2 times 2, 2 times 3, etc. And when you start writing them out like that, you realize what the phi should be that's one-to-one and onto. So this means when I think about writing out that formula, phi of n equals 2n is a one-to-one onto map, a bijection. That means even though there's a lot more numbers than there are even numbers, those sets are kind of the same size. It's a bijection from n to the set of even n. It's one-to-one and onto. That's what bijection meant. So we think of those infinite sets as being the same size. So think these two infinite sets are the same size. I'll put that in quotes because we got to. And Cantor invented a word for that kind of size, and he called it the cardinality. They're the same cardinality. Okay, so that's surprising. I guess I should mention a few words since I'll be blurting them out from time to time. So there's some words. S is called denumerable. If it's an infinite set, and it can be put into one-to-one correspondence with the natural numbers. It basically means you can count them, count the elements. Is infinite, and there exists a phi from the natural numbers to S that's one-to-one and onto. Okay, that's one word. And another word is S is countable. Means it means it's either finite or it's denumerable. And that really does mean you can count it with your fingers. It just, you might need infinitely many fingers. S is countable. If S is finite. Or in the case that it's infinite, it's denumerable. Once you know the word countable, you almost never say denumerable again. Okay, so the big question is anything out there not countable? And so you might think, okay, I got to make let's try to make something even bigger than let's see, n is bigger than the set of even numbers. I want to make something that's trying to be bigger than n. And here's the next example, which is the classic thing in all the books. How many people have seen this stuff before? Some. Yeah, I kind of read it in high school in an encyclopedia. There was a wonderful article in the Encyclopedia Britannica, and it fired me up. It wasn't until I started taking classes in mathematical logic and set theory that I got the full picture. So next, let's consider n cross n. Of course, that's the Cartesian product. That's the set of all ordered pairs, n, m, such that n and m are in n. Okay, let's think about that. How would I count those? And there's a very natural way to count them. I would put them in a grid. 1, 1, 1, 2, 1, 3. I want to make sure I get all of them this way. 1, 4, etc. And then 2, 1, 2, 2, 2, 3, 2, 4, etc. Dot, dot, dot. Next one would be 3, 1, 3, 2. I'm going to list them all this way. You agree that eventually, if you give me an n, n, I could point to the spot in the grid where it occurs. Let's see that. 1. It's like an x and a y coordinate when you think about it, etc. I guess I have to do one more row. Do I? Why not? 4 comma 1, 4 comma 2, 4 comma 3, 4 comma 4. And I'm going to have a dot, dot, dot going this way and a dot, dot, dot going up too. I have now listed all the elements of n cross n. If I told you to count them, how would you do it? You see somebody, yes, that's my favorite way to do it. The book has a different way to do it, which I'll let you read about. Let's try purple. How would I count them? I'd start, go like that, and then it's kind of like doing a determinant of a matrix. I'd go like that, and then I'd come back and do the next diagonal, and then I'd go down and do this diagonal, etc. Okay, so this would be 1, 2, 3, 4, 5, etc. 6. And eventually I'll plow through all of them that way. So you say, even if pick an n comma m, where both the n and m are gigantic, I could tell you how long I'd have to do this before I'd hit it. So eventually I'm going to hit them all. And that's a one-to-one onto map of natural numbers, one-to-one onto n cross m. Anybody not believe that? So the aha, what? That's weird. The aha is this phi maps the natural numbers one-to-one onto n cross n. So even though that set, that grid, looks like infinity times infinity if you're thinking about area. The x-axis is infinite, the y-axis is infinite, and so you think that this is infinity times infinity. Why didn't I see what happened, sorry. That's one-to-one onto. And so what something weird's happening here that you never saw before. This is size infinity. This one feels like size infinity times infinity. I'll put quotes around that because it doesn't mean anything. Cantor is trying to make sense of what that means. So exclamation point. So they're the same size. And fascinating, if you look at those and think about them, they're kind of like listing out the rational numbers. Let's think about the same thing for rational numbers. So the example next, I'll take the positive rational numbers, Q plus. Oh, let's see, how would I list those out? I'd start with 1 over 1, 1 over 2, and 1 over 3, etc. 1 over 4. That's probably enough. And then I would have 1 over 2, 2 over 2, 3 over 2, 4 over 2, etc. And guess 1 over 3, 2 over 3, 3 over 3. And you realize, oh darn, I'm repeating some of this stuff. 4 over 3. So dot, dot, dot. And then dot, dot, dot going up. Well, you realize, oh, this 1 over 1, I would be smarter if I wrote that as 1. 1/2, 1/3, 1/4, that's great. Nothing else I have to, well, when I get to, yeah, those are great. Then 1/2, 1/2 appears in the bottom column, so I'm going to cross it out. 2/2 is 1, so I'm going to cross it out. 3/2 is something new. Never occurred before. 4/2 is 2. Did it occur anywhere? No, it's new. But I'll change it to 2. Etc. And I can now go through the next column, the next row, and do the same things. 3/3, it's already in the list. I'll cut it. 4/3 is a new thing. And I'll keep doing that. And then I'm going to slide them all over. I cross out the ones that repeat, and I slide them all over. Remove the crossed out ones. Remove the crossed out ones, slide over. And now do the same old zigzag counting thing. Count with the zigzag method. We see that Q plus is the same cardinality as the natural numbers. Even though when you think of the real, the positive, the rational numbers on the positive real axis, it's really dense. They're all over the place. It looks like there's lots and lots of them. But it's the same size infinity as the natural numbers. See that Q plus is countable. Read carefully what the book says about this, because they use sort of a more abstract mathematical argument. I like mine with my bare hands where I just do it and you believe it. CQ plus is countable, even though it looks really big. I'm going to mess around and show you some kind of classic things you can do. Let's think about let's how to show that all the rational numbers Q is so Q and N have the same cardinality. Let's see, how would you do? We show that Q plus is countable. So here's, if you think about this for a while, here's what I would do. I would start with the even numbers. That would be 2n. So the even n's would be 2n, etc. And then the even n, we know, are the same size as the n. I can get a phi going from that. And then I can get a map that goes from n to q plus. I just showed you how to get it. And I could do the same thing with the odd n. That's one-to-one onto the natural numbers. Let's see, what would the map be? It would be going this way, would be 2n minus 1. So this map was going this way. That's 2n. Going this way, it would be 2n minus 1. That would map the natural numbers one-to-one onto the odd numbers, 1, 3, 5, etc. Okay, so that would be a bijection. And of course, Q plus is bijective with Q minus. So I could map that to Q minus. Does that now I say, oh, well, so now I see, since I know that the even and the odd, of course that's n. So I've made a one-to-one map. I can make a one-to-one map from the natural numbers to Q plus union Q minus. Oops, that's not all the rational numbers though. I missed one. 0. how can I make 0? How can I get 0 in there somehow? Ideas. If I had to make you an explicit one-to-one map here, how could I do that? Yeah, exactly. Yeah. My personal choice was to skip an odd number. That would be, the first odd number is 1. And so it feels good to skip the 1. So I see that n is the same size as q plus union q minus. And to get the 0 in there, here's something to do. So I'm thinking out loud here. If I take phi of n equals, instead of 2n minus 1, 2n plus 1. That would map phi to n. And let's see, the first one would be 3, 5, 7, etc. And so I'd get a map to the odd numbers minus 1, and I could pull out that 1 and have it mapped to 0. Okay. So I'd have here even, odd, greater than or equal to 3. That would be equivalent to q plus. Odd greater than 3 is the same as n, so that could make that equivalent to q minus. And then I'd have the first odd number, which is 1. That's the one I tossed out. That would be the same as mapping to 0. So these three combined to be equivalent to the natural numbers. They are the natural numbers. And these three combine to be all of q. So q is the same size as n. Okay, that little trick of messing around, shifting stuff, that's a standard trick, and the book describes it carefully. And so, if you're off by a finite number of things, you can always monkey around and shift these things and fix that fact. And also a trick I showed you of throwing out the ones that repeat, that's a standard trick also. But it's surprising how subtle some of these arguments are. There's a famous thing called Bernstein's theorem, which is, it uses only intuitive facts, but it's still long and involved reasoning. And you have to read it a few times before you believe it. Anyway, we're not going to dive into the really subtle things at this point. But I will mention there's some tricky little arguments to show various things. So tricky little arguments. Show, here's a famous thing to show, called a theorem. Suppose I've got two sets. I'll call them S1 and S2 are sets. And S1 is contained in S2. Kind of an easy thing everybody would believe is that if S2 is countable, then of course S1 has to be countable because it's inside, and so it has to be smaller, which means it has to be finite or also countable. If S2 is countable, so is S1. Everybody believes that and wouldn't even think about that it's a hard thing to show, but to actually sit down and show it would take enough time in the class that I'm not going to do it. You can find it in an appendix of the book. And it's not a difficult thing, it's just a time-consuming thing. And you have to be very careful about how you talk about it and do it. And see, what's the other thing? If the first one, the smaller one, is uncountable, then of course the bigger one has to be uncountable too. if S1 is uncountable, then so is the bigger one. Okay? Another little tricky thing that I'm not going to dwell on is the following are equivalent. Let's see, 1, S is countable. This is very related to the previous theorem, which means it's finite, or you can put it in a one-to-one correspondence with the natural numbers. Okay. 2, there exists a phi which maps the natural numbers onto S. That's kind of like counting them. And then another one is there exists, I'll call it a psi, that maps S one-to-one into the natural numbers. Okay. If you think about those for a little bit, you believe them. But to actually demonstrate them is tricky, but not terribly deep. Questions about that? If I was going to show, how would you do this in words? Let's say I have a map of N onto S. Okay, that means I'm going along counting stuff, and then I I already counted that one. Throw it out. Okay, so I could go from my onto map to one that's one-to-one and onto. When I'm counting along and say, I already counted that one. Throw it out. Go to the next one, and keep throwing it out until you exhaust the set. Having an onto map would allow you to do that. So it'd be kind of like when I did the rational numbers and shoved them over by tossing out the ones that repeat. It's exactly that argument. Okay. A similar fact, let's see, the theorem is that, the important theorem is that a countable union of countable sets. So far it looks like nothing's going to be bigger than countable. Everything I've shown you is countable. Even a countable union of countable sets is countable. I've kind of done the proof already. If I was going to, here's a sketch of the proof. Let's say I have a bunch of countable sets. A1, I would list out, counting means I can list them out. A11, A12, A13. The second number is the counting number. And A2 is A21, A22. Some of these might be finite, but let's do when they're all infinite case, because that's the one that is more mind-blowing, etc. A23, ... All right, one more. A31, A32, A33, ... And then I do the zigzag counting thing. So I go down, back, down, etc. Count them. And that would give you a one-to-one onto map to the union from the natural numbers. Okay, so right now it's looking like, okay, all infinities are the same. But Cantor realized there's infinities that are bigger. And people had a hard time buying his research and his papers. And I don't know, he became very depressed at some point in his life. And actually had to be institutionalized. But he discovered that the real numbers, even between 0 and 1, the bigger infinite set. I'll put bigger in quotes. I guess I should say is bigger. And it's a very fun argument. Let's say I could count the real numbers. Then I would have R1, R2, real number 2, real number 3, etc. And let's see, my real number 1 would have a decimal expansion. So it would be point, digit number 1, digit number 2, digit number 3, etc. Digit number 4. My second real number, it would be point, digit number 1, digit number 2, digit number 3, digit number 4, dot, dot, dot. It could be that all the rest are zeros, etc. And then the third one would be D31, D32, D33, etc. D34, dot, dot, dot. And now these go forever. The dot, dot, dot. Okay, so if there was an enumeration like that, every real number has a unique decimal expansion. And so Cantor said, well, how could I miss something? And he had this fiendishly clever realization that, okay, I'm going to go down the diagonal here. I'll circle my diagonal entries. Okay. This is called a diagonal argument. And Cantor was the first one to use it. Okay, so I'll have point, I'll call it capital D1, capital D2, capital D3, dot, dot, dot. Okay, the diagonal, I'm going to take capital D1 is just going to be any old digit that's different from D11. So D11 is a different number, different integer between 0 and 9. Is different than D11. D2 is different than D22. That's the diagonal. And D3 is different than D33. Etc. Dot, dot, dot. And the mind-blowing thing is that this number, let's call this D. This number doesn't get hit. D. D does not get hit by the map, by the phi. What's the phi? The phi sub n is the r sub n. And so finally, I found an infinity that's bigger than the natural numbers. And in fact, the whole real line would be even bigger. Okay, and the cardinality of the whole real line is called the continuum. And a big, a mind-blowing conjecture is that it's called the continuum hypothesis. Is that there's nothing that you can squeeze between the integers and the whole real numbers. That's the continuum hypothesis. And Ralph Cohen finally proved it in my lifetime, which means a long time ago. That was a mind-blowing thing, and of course he became very famous overnight for that. Very famous. It's a very subtle thing and is related to things like the axiom of choice and mind-blowing set theory. But I'll talk more about that in a minute. And now the big question is, are there things that are even bigger kinds of infinity? Of course, if you find one that's bigger, then probably there's even bigger ones. But R cross R also is the same size as R. So now I'm going to get wild and crazy and not really for a minute. R cross R is the same size as R. And actually Cantor proved that, and he couldn't believe, and he's kind of hard time believing it himself. But he couldn't deny that his argument was correct. So it's just like n cross n. But trickier. You had to work harder to show that. Okay, so how do you get bigger than big? And so Cantor realized that if you give me a set, the set of all subsets of that set is bigger. So Cantor's brilliant breakthrough. Let's say we have a set A. P of A is called the power set of A. I'll explain where that word power comes from in a minute. And the power set of A is the set of all subsets. Of A. Note that the empty set is a subset of A. So the empty set's in the power set of A. And of course the set itself is in the power set of A. Cantor's theorem is that the power set is always bigger than the set. A is bigger than A. I'm using bigger in quotes. So there is no one-to-one onto map. There is no phi that maps A one-to-one onto. That would mean that those two things are the same size. And here's what it means for P of A to be bigger. And so, in fact, in Cantor's theorem, in fact, there is no phi. A is small enough that you can't map it even onto P of A. So there is no, which is onto, just onto. Okay, that's what it means for the right-hand side to be bigger than the left-hand side. If you can't plaster A on top of P of A. You plaster A on top of P of A, and you've always got stuff left over that you can't hit. So everybody believes that's what it feels like to be bigger. Cantor was the one who put that notion into words. Let's see, and his proof is very simple and fiendishly clever. Kind of like the diagonal argument we did above here. Proof suppose we had a phi mapped A onto the power set. Okay. Well, A's are things, and P of A's are sets. A is a set of things. So this is what call this D because it's kind of like diagonal. We let a set D be the elements of A such that A is not in phi of A. It's kind of like changing that digit. And that's why it's called D for diagonal. Okay. Well, if that map is onto, then that's a set. No, D is a set, a subset. D is a subset of P of A. It's a subset of A. So D is in P of A. Okay. And it gets hit. If phi is onto, so there exists an A naught that hits it. So there exists A naught, an element of A, with phi of A naught equal to D. And now the big question is, what the heck is A naught? So this is where Cantor realized he had something here. Is A naught in D? Or is A naught not in D? Think about it. You can get a very quick contradiction in both cases. So here's a fact. It's either in or out. Fact. A naught is either in D or A naught isn't in D. If A naught's in D, so the case, A naught in D, what does that mean? That means, what does it mean? It would mean that A naught is not an element of phi of A naught. But phi of A naught is D. So contradiction. That doesn't make any sense at all. So I mean, remember D was a set of points such that the point is not in the phi of A set. And so it's by the definition of D that I've written that thing. That it's A naught is not in phi of A naught. Okay, the next case is A naught not in D. Okay, the book was very terse at this point, and I had to read it twice myself, even though I know this argument in my sleep. Let's see, so if A naught is not in D, then it's not the case that A naught is in phi of A naught. And of course, phi of A naught is D again. And we get the same stupid contradiction. If you've ever heard of Russell's paradox, it's kind of like that. In fact, Russell's paradox is highly related to this whole subject in business. Okay, so because I've got these contradictions mean that there couldn't have been such a phi. Contradictions means that no such phi exists. And now I can get arbitrarily big things. I take the power set, it's bigger. I take the power set of the power set, it's even bigger. And I can do that forever. And set theory is studying just how crazy and wild you can get by doing stuff like this. And it's rather subtle because things like the axiom of choice and philosophical questions like that become very critical and important in understanding these things. Anyway, I think this is a lot of fun, and